Oh, hey there, kids. Nathaniel, the chemistry newscaster here, but as you already know, you can call me Nate News. Today we have a very special episode for you, an episode on, drumroll please, trends in the periodic table. I could talk for hours about this enthralling topic, but how about we hear from a few special guests? First up, here's your favorite chemistry-themed rapper, DJ Donnie. Hey there, Nate News. Thanks for passing me the mic. I hope you kids are ready for some absolutely redonkulous bars. And if you're not sitting already, I recommend finding a seat.
First, let me put on some goggles so that I have some credibility. How about we start off rapping about electronegativity? Just like mine rap, this topic's nice and clean. I'll tell you how we're getting values from francium up to fluorine. How about we start off with a simple definition? Electronegativity tells us how certain bonds come to fruition. This value can go from practically 0 all the way up to 4. If the atom's got a high number, it wants electrons more. The highest values are found in the top right of the table, like the 5 on the screen. If you're watching Fox on cable, as you go down to the left, the values get smaller. These numbers get teeny tiny, like Boston's favorite baller. Top right has the greatest nuclear charge and atomic size, and going down and to the left, atomic radius starts to rise. This is why atoms like fluorine tend to have a greater pull, and don't worry about helium or neon, whose electron levels are full. Why does this even matter? A question to which I'll respond. The difference between two atoms determines how they will form a bond. The atoms can share electrons if they want them about the same. I should remind you of preschool values if you think that sharing's lame. The more electronegative element brings electrons a little nearer. That creates polarity. Now just one thing to make clearer. The bond is ionic. If the difference is greater than 1.7, the atom stops sharing, like a mean kid named Kevin. The more electronegative element takes the electrons and a charge, creating a bond with the positive ions, and strength can be quite large. That's all I have on that, so for now I'll have to quit. I hope you did not think my rhymes were a steaming pile of garbage.
Wow, you kids and your hip-hop. Unbelievable. I thought that last line was going in a totally different direction, and for the sake of our viewers at home, I'm glad it did not. You can ask anyone around here. I was busting a move while you were delivering those ill rhymes, and I'm sure the kids at home were too. I heard you talk about atomic radius and effective nuclear charge, so could you possibly spin a few dope lyrics on those topics? Oh man, I would love to, Nate News.
For effective nuclear charge, think electronegativity. The trend is all the same, just like electron affinity. We'll cover that last one later, but let's not go there now. Let's talk about electrons staying in atoms and most importantly how. These negatives get pulled by positives, and you find those in the nucleus. Without enough nuclear charge, the atom explodes, like Vesuvius. As you move to the right, protons increase and so too does nuclear charge. But once you go down, sublevels increase and shielding becomes rather large. When we discuss nuclear charge, we're talking about the valence ones, electrons that chill on the outside, like Pluto to the sun. See, in between the valence and the nucleus lies a few electrons. We tend not to worry about these, they're the chess equivalents of pawns. But as these shields increase, effective nuclear charge goes down, like my chances of not crying whenever I see a clown. That's why as you move down the table, nuclear charges just decrease, but as you already know, more levels is really just a piece. As you move to the right, the number of protons goes up. That increases the pull on the valence. Now you know what's up. Now a bit about atomic radius. The trend is just a reverse. I've been killing these rhymes so hard, you'll have to take them out in a hearse. This radius increases as you go left and down. Effective nuclear charge goes down, so francium gets the crown. The crown for being really large, if that wasn't clear. Just remember these trends are opposite. Bigger charge makes atoms smaller. If you remember these lines, you're on your way to being a scholar. I hope you've enjoyed my rapping. I think it was pretty great. It's almost time to pass it over to everyone's favorite mate.
I get it. You said mate because he's Australian. You never cease to amaze me with your rambunctious rhymes, DJ Donnie. Now here's our favorite Australian mate, Kangaroo Kev, with a field report.
Yeah, alright, thanks for passing it over, Nate News.
folks. I'm out here in the beautiful fields of Perth, Australia, and I'm just dying to teach you a few things about chemistry. First things first, something DJ Donnie mentioned before, electron affinity. If you have an affinity for something, it means you want it. With that in mind, electron affinity is how much an atom wants an electron, or how willing that atom is to take that electron. An atom would want an electron so that it could get to a more stable energy state, like a more full outer energy level. So as you go across the table, electron affinity increases because the atoms that are closer to having full octet want electrons more because they want to be more stable. I could go more into the releasing of energy and things like that, but I think that's enough on electron affinity for now.
Good stuff, Kev. It always amazes me how funny sounding you are. Let's hear a little bit about our last topic, ionization energy.
Alright, I'm just gonna ignore what you said about my voice and talk about ionization energy. This really has to do with effective nuclear charge. Ionization energy is the amount of energy needed to take an electron out of an atom. If that nucleus is holding in the valence electrons with a large force, then the ionization energy will be quite high. The opposite is also true. Therefore, as effective nuclear charge increases, so too does ionization energy. For a second here, let's think about these blades of grass as valence electrons. Now let's think about this one right here, this phrase. Alright? The valence electrons experiences a very small nuclear charge because of all the shielding and because of how far away it is from the nucleus. For that reason, I can take a blade of grass away pretty easily. This is like a valence electron in the francium, right? However, let's think of this blade of glass as a valence electron of fluorine. Not a lot of shielding relative to the charge of the nucleus, so it's going to be really hard to take away an electron. See? Pretty tough. That's why you really never see fluorine giving away too many electrons in nature. That's all I got, Nate. Back to you in the studio.
Thanks, mate. Alright, kids, that's all we have today. I'd like to thank DJ Donnie and Kangaroo Kev for making all this information fresh for you kids at home. We'll see you next time. Thanks for watching.